Hello students, welcome to the lecture number 51 today. In today's lecture we will discuss some more numericals regarding bending stresses in the beams and our flexure equation. So just practice these numericals. For your practice we will consider rectangular section, hollow rectangular section, the unknown stress, a cantilever beam, etc. So let us start the example number 14.12. In this the beam is cantilever as shown in figure. What is given in the data, you can see a cantilever beam is rectangular in section having 80 mm width and 120 mm depth. If the cantilever is subjected to point load of 6 kN at the free end, so here it is subjected to 6 kN point load at the free end of cantilever beam. This is the front view having length L meter, which is not given in the data. 80 mm is the width of the section and 120 mm is the depth of the section, which can be visible from the side view. Now at the centroidal axis the bending stress is always 0, and at the top layer and at the bottom layer the value of the bending stress will be equal, which is which is compressive at the upper layer and which is tensile at the lower layer. Stresses is not to exceed 40 megapascal, so value of bending stress is given 40 megapascal. Sigma max means 40 Newton per mm square. Find the span of the cantilever beam. So we have to find the span, means length of the cantilever beam. Let L equal to span of the cantilever beam. First of all, we will calculate Z. Z means our section modulus. So what is the formula for section modulus for rectangular section? It is BD square by 6. Here B means width, which is 80, and D means depth, which is 120. So 80 into 120 square by 6, 192 into 10 raised to 3 mm cube. So here it is the section modulus for this particular rectangular section. Let us see ahead. Now we have to find bending moments. Hence it is a cantilever beam. So bending moment will be load into distance up to fixed end. Okay, load is acting at the free end, and the fixed end is covering the entire span of the beam. So now bending moment equal to W into L for such type of cantilever beam. So W means 6 kN, so 6 into 10 raised to 3, well, length is not available to us. Now as per our bending or flexure equation, sigma equal to M by Z. So sigma is already available, 40 M by Z. M means 6 into 10 raised to 3 into L, which is calculated over here, divided by Z is 192 into 10 raised to 3, we have calculated earlier. So final answer or simplification will give you L by 32. By cross multiplication, L is equal to 40 into 32, which is equal to 1280 mm. So 1.28 meter. So this is the length of the cantilever beam, which is 1.28 meter. So again and again we are using just three formulas. First formula, sigma equal to M by Z, which is our flexure equation, main equation. Rest two formulas, in which first formulas are section modulus Z is equal to I by Y, or we can directly calculate for the rectangular section and circular section, BD square by 6 and pi by 64 d cube, pi by 32 d cube, sorry. And now last sum is of cantilever beam. So bending moment is the second formula, which is changing W into L. In case of simply supported beam subjected to central point load, it is WL by 4. And in case of simply supported beam subjected to UDL on entire span, the moment is WL square by 8. So these are the several formulas which you have to remember to complete this type of numericals. Let us see one more numerical. A rectangular beam, 60 mm wide, 150 mm deep. So here you can see in the figure the beam is 60 mm wide and 150 mm deep. Simply supported over a span of 4 meters. So here it is simply supported beam. First reaction is RA, second reaction is RB, and length is 4 meters, which is known as span. If the beam is subjected to uniformly distributed load of 4.5 kN per meter, so UDL is given to you 4.5 kN per meter. Find the maximum bending stress. So we have to find this bending stress at the upper layer and at the bottom layer. These two values are exactly equal because of the symmetricity of the figure. At the neutral axis, bending stress is again 0. So now we are interested in calculating the sigma B, bending stress. UDL is 4.5 kN per meter, which is also equal to 4.5 Newton per mm. As kilonewton is 10 raised to 3 Newton and meter means 10 raised to 3 mm, so 10 raised to 3 will be cancelled out. And span L equal to 4 meter, which is converted into mm, so 4 into 10 raised to 3 mm. Depth and width are already in mm. So we are doing the numerical in mm only. First of all, as usual, our section modulus is for the rectangular section BD square by 6. B means 60, D means 150. So answer will be 225 into 10 raised to 3 mm cube. So here it is the section modulus for this beam. Now what again? We have to find bending moment and then applying the equation sigma equal to m by z. Okay. So now let us start with the next calculation. You can see this is the calculation for bending moment and bending stress. Bending moment is equal to WL square by 8. As I said, it is the bending moment for simply supported beam of UDL acting on entire span. So WL square by 8. W means UDL, which is 4.5. L means length of the beam, 4 into 10 raised to 3 whole square as it is. So the simplification will give you 9 into 10 raised to 6 Newton mm. Now bending stress is m by z. M is as earlier 9 into 10 raised to 6. Z is calculated in the previous page 225 into 10 raised to 3. So answer is 40 Newton per mm square, which is equal to 40 megapascal. So very simple sum. In the first numerical, we have to calculate the length of the cantilever beam. In the second numerical, we have calculated the bending stress for the simply supported beam subjected to entire UDL, entire span, UDL on the entire span. So now let us take one more example. This is exactly similar type of example on which in simply supported beam having two support reactions RA, RB, UDL is acting 20 kN. But here what is written 20 kN uniformly distributed over a span of 3.6 meter. So span is 3.6 meter but UDL is 20 kN. So we have to write over here 20 kN per meter. Okay. Now the depth of the beam, here the most important terms is coming. Depth of the beam section is twice the width. So depth means this depth is 2 times of B. B means width of the section. So width is B and depth is 2 times B. Okay, this type of relation is given for the cross section dimensions and we have to find these dimensions. Maximum bending stress is 7 megapascal at the top and at the bottom there respectively. Find the dimensions of the beam section, means we have to find beam width to be and beam depth to be and beam width B. Ultimately we have to find B only. So first step, Z. Z is our section modulus. For the rectangular section it is again BD square by 6, but this time B remains as it is. D means replacing by 2B whole square by 6. So simplification will give you 2B cubed by 3. 2B cubed by 3. So finally bending moment M is equal to WL square by 8 because the beam is simply supported and subjected to UDL on entire span. So final answer will give you W into L by 8. Here W into 1 time L becomes capital W, which is total load 20 kN. So we can consider like this 20 into 10 raised to 3, or you can go with our usual method also. It will give the same answer. So length equal to 3.6 into 10 raised to 3, 8 will remain as it is. So final answer is 9 into 10 raised to 6 Newton into M. Again Z and M available. We have to calculate the dimensions. So applying the flexure equation. What is our flexure equation? Sigma equal to M by Z. Sigma is given to you 7. Bending moment we have calculated 9 into 10 raised to 6. What is Z? Z equal to 2B square by 3 as per earlier simplification. So now B cube remain as it is, and by simplification we will get B cube equal to this term, which is equal to 1.93 into 10 raised to 6. So by taking cube root you will get the answer 1.25 into 10 raised to 2. So multiplying we will get and removing the decimals. So 125 mm is the width of the beam section and the depth is 2 times the width, means 2 times 125. So answer is 250 mm. So here it is the width and depth of the particular beam section. So this is the third numerical. In first numerical, length of the cantilever beam is not given. In the second and third numerical, two beams same to same, simply supported, entirely subjected to UDL. But in the first case we have to find bending stress only. In the second case we have to find unknown cross section dimensions. Let us now see one more numerical for the hollow rectangular section. What happens with the hollow rectangular section? This is very important numerical, you see. Example 14.50. A hollow square section with outer and inner dimensions of 50 mm and 40 mm respectively. You can see this is the hollow rectangular section. The outer depth is 50 mm and the inner depth is 40 mm. It is square, so horizontal dimension is also 50 and inner horizontal dimension is 40. So it is the square cross section. The beam is cantilever of span 1 meter. So here it is the cantilever beam of length 1 meter subjected to point load at the free end. So again bending moment will become W into L. Bending stress is maximum 35 megapascal at the outer edge. So 35 megapascal at the top and bottom layer respectively. So what we have to calculate, how much concentrated load can be applied at the free end of the cantilever beam. So we have to find this load W. Okay. Now W is the concentrated point load at the free end. Now how to calculate bending moment or say moment of inertia. Moment of inertia is very much important for the rectangular or square hollow section. You know, for the square section the moment of inertia is BD cube by 12. Here it is written capital BD cube by 12 because the section is hollow. So from this capital BD cube by 12 we have to subtract small BD cube by 12 for the inner square. Now it is a square section, so B and D in both the cases are equal. So just replacing capital B as it is and in place of D replacing capital B again. So B into B cube by 12. Similarly for the smaller square B into B cube by 12. So answer is capital B raised to 4 by 12 minus small b raised to 4 by 12. So capital B is 50 now and small b is 40 now. So by the simplification 307.5 into 10 raised to 3 mm raised to 4. Here it is the answer of moment of inertia for the hollow rectangular section. What is Z? Z equal to I by Y, where I is calculated over here and Y means what? Y means from the center of gravity to the top layer or bottom layer you can say. So from the center of gravity to the top layer is half of 50. So 50 by 2 means 25. So Y equal to 25 written over here. By doing the division we will get 12,300 mm cube, which is the value of section modulus. Now we are interested in finding the load W. So our main equation is for the bending moment and bending stress. So M equal to W into L because the cantilever beam is there and subjected to point load at the free end. So W into L means 1 into 10 raised to 3. 1 meter is given to you. So 1 into 10 raised to 3 mm. So final answer is 1 into 10 raised to 3 W is the value of bending moment. Now our flexure equation is sigma equal to M by Z. So sigma is given to you 35. Bending moment is 1 into 10 raised to 3 W and Z is equal to 12,300. So W is equal to 35 into 12,300 upon 1 into 10 raised to 3. So answer is 430.5 Newton. So this much amount of load is acting at the free end of cantilever beam. So this is one more variety in which load is not given. Furthermore, section is hollow square section. So this type of many numericals you can design and you can practice. In the next lecture, we will find the bending stresses for the I sections or T sections. And that is our last lecture on Monday. So till then, practice these numericals. We will see the I section and T section on Monday and conclude this chapter. So till then, goodbye.